Alright guys, today we'll be discussing about the glycogen synthesis and the glycogenolysis. So first we'll develop the glycogen, so we'll synthesize the glycogen and then we'll break it down. First you have to understand that when we do consume a lot of glucose, all those glucose, not all of them, but the glucose which will be excessive, those will be converted into glycogen. Now what is glycogen? Glycogen is a amylopectin. It means a branched molecule of the glucose. So let's see how that is synthesized and broken down. So the very first step. Now, as you remember from glycolysis, again, we had this glucose, and then the glucose were converted into glucose 6-phosphate. I'm not going to draw again the structures because we already know them. And the glucose 6-phosphate were converted into pyruvate as a last product, of course. So this is it, glycolysis, what happened. Now, here, what will happen then? In this term, as we use more glucose, consume more glucose, the glucose 6-phosphate here, it will be converted not to fructose 6-phosphate, but it will be converted into glucose 1-phosphate. It means then an isomerase, a mutase enzyme, a mutase enzyme will come and will transfer the phosphor to first carbon of the glucose, so the glucose will be glucose 1-phosphate. Now from here, the formation of the glycogen will start. Now let's go here. Now, in order to make the glycogen synthesis, guys, we do need a very primer molecule. So that primer molecule is a protein enzyme which is called glycogen. So before reaching to that step, let me explain you how and where we need that glycogen. So here is the glucose 1-phosphate. Let me draw it. 1, 2, 3, 4, 5, and 6. And in glucose 1-phosphate, we already know that the phosphor is located in carbon number 1. So glucose 1-phosphate. Now what's going to happen next? Actually, the next reaction is interesting. Let me tell you how it is interesting. Here, guys, an enzyme will come, which is a phosphorylase enzyme. So it is a phosphorylase enzyme. Now this phosphorylase enzyme is actually going to add here and remove from here some phosphor. See, adding and removing, I'm saying. Now that's how it's going to happen. Actually, this enzyme is going to take the UTP, which is uridine triphosphate, which is a nucleotide, and it's going to add this UTP into glucose 1-phosphate. But there's an issue. When it's adding the UTP, it's actually taking out or removing 2 phosphor of the UTP here, one normal and one inorganic phosphor. So P plus Pi. So 2 phosphors of the UTP will be now removed. Now, as you understood here, if we remove from UTP 2 phosphor, it will be converted into UMP. So the UMP is now added to glucose 1-phosphate. But let's see what happens. So this is glucose 1-phosphate. Now, as we add this UMP to the molecule, actually it's going to bind with the phosphor, which is located at the carbon number 1 of glucose. So the UMP here again will be converted into UDP. So our molecule now will become UDP glucose. Hope you understood. See, the first carbon, which is first phosphor, which is located at the first carbon of the glucose 1-phosphate, that is now added to UMP. And from UTP, let me show it here. From this UTP, 2 phosphor were removed and the UTP were converted into UMP. So the UMP now took the carbon, took the phosphor from the first carbon of glucose and it's converted into UMP. And with this, we have 2 different molecules, UMP plus glucose here. So it's the UMP glucose. Now, let's see what happens next. So this glucose here, which is formed by the phosphorylase and other enzymes. Now, by the help of an enzyme which is called glycogen synthase, or even without any enzyme, it could happen also, glycogen synthesis, here the glucose will be converted into glycogen. Now, how it's going to happen? Actually, the glycogen synthase here, it will take a molecule which is called, it's going to add this glucose to a molecule, to a protein which is called glycogenin. The glycogenin itself is a enzyme. So here, now the glucose will be added to enzyme which is called glycogenin. It's a protein. So as the first glucoses are added to glycogenin, there will be a formation of primer glycogen. So as we have this primer glycogen, imagine this is the glycogenin, and here we have these molecules of, glucose. So here, these are the glucose which is now added to glycogenin by the help of glycogen synthesis, or without that. Now this is the primer glycogen which is formed here. Now to this primer glycogen, the other glucoses will come and they will bind with each other, and they will form this glycosidic bond, and it will start growing. Now first let me show you how that happens, and then I'll go to detail. So this is the second glucose which are coming, and they're just binding with each other, making this structure which is called the glycogen. So these are very straight glucoses which are binding with each other, and then there are some branched glucoses which are coming from side, and they're making the amylose to amylopectin. So the glycogen is now formed as amylopectin because this is the straight or the linear glucose linkage, and now we have this branches here. So these branches are also done by specific enzymes. Now let's go and see how these branches and the glucose which is binding to the first or to primer glycogen happening. So now imagine we already have this glycogenin with glucose, and this is the glucose residues at the glycogenin molecule. So this is the glycogenin, let's say. Now here we have the first carbon, and on the first carbon we know that in alpha configuration we have the hydroxyl group and hydrogen here. So what am I going to do? I'm going to take this, copy, and paste. So enter. There's again the same type of glucose here, which is in alpha form. Now what's going to happen is here that from the carbon number 1 here to carbon number 4 here, the linkage is going to happen. So the hydroxyl group of the fourth carbon is going to react with the hydrogen of the first carbon. So they're binding with first carbon and 4 carbon of the second glucose. So they're making this alpha 1,4 glycosidic bond or linkage. So this is how the linear glucose is forming. So this is the glucose which we are discussing. And then what happens? That in some cases there are formation of branches, and those branches, let me show you. So this is the linear glucose now, and let's say here is the first carbon, and remove this. This is our second glucose, which is going to make the branch, and here is the sixth carbon. So what's going to happen then? This second glucose, which is going to make the branch of the glycogen, it's going to come and bind with the first carbon here. So again, the reaction is same. Here we have the hydroxyl groups, and here we have the hydroxyl groups, and they will form here the water, and a glycosidic bond will be formed. So this bond here at the branching section will be formed between first carbon, alpha 1, and sixth carbon of the second molecule, which is the 6, and glycosidic bond. So in order to synthesize the glycogen, we needed a primer, and that primer will be glycogen. Next, we needed to elongate their size. So the elongation happened, or elongation of the chain of glycogen is done by alpha 1 for glycosidic enzyme. I'll just name it. And then there were necessity to branch them. So branching, I mean the elongation also is like branching, guys. But here, what I mean by branching is like the side branch. So let me make it more specific. That the side branches were done by the alpha 1 and 6 glycosidic bond. So those enzymes which are elongating the glycogen and side branching the glycogen, those are in a group. They are called the branching enzymes. Branching enzymes, and those are 1 alpha 4 glycosidic and 1 alpha 6 branching enzymes. So this is how the glycogen is now formed. Now let's move to glycogenolysis. Now let's see how we can break down the glycogen. Now it's a very important topic here, so listen carefully. See, this is the linear glycogen here I'm drawing. And here I have the glycogen. And then let's say at this point we have the branch. So that's the branch which is formed now. After the branch forms, the branch also starts becoming linear and elongates. So here we have the elongation again. Now, these two ends, guys, these are called the non-reducing end of the glycogen. Now, the non-reducing end of the glycogen could be several, guys. It doesn't matter. It's not one. Let me show it. See, all of these are non-reducing ends. Now, what I want to explain is here that we have only one reducing end, which is near to glycogen. So in order to break down this molecule into pieces again and form glucose, we do need some specific enzymes. So glycogenolysis is important topic here, yeah? Now, at the first, you have to know that there is an enzyme which is called glycogen phosphorylase. Glycogen phosphorylase. Now, this enzyme is actually positively stimulated or activated by another enzyme, which is called glycogen phosphorylase kinase. So, glycogen phosphorylase kinase, or phosphorylase kinase. Now, what's going to happen here? That here, actually, the glucagon when you are fasting will increase. And as the glucagon increases, it will stimulate the cyclic AMP. The cyclic AMP will stimulate the glycogen phosphorylase kinase, and the glycogen phosphorylase kinase will activate the glycogen phosphorylases. So this is the pathway how the phosphorylase is activated. Now, why it's important, because in deficiency of glycogen phosphorylase kinase or glycogen phosphorylase, there will be development of different disease. Now, let's move on. Let's see how these enzymes will be breaking down our glycogen. So this is our glycogen here. Now, appreciate that this is the non-reducing end, and here we have the branching side. Branching side. So at the very beginning, as the phosphorylase enzyme is activated, so this is the phosphorylase enzyme. Phosphorylase enzyme. Now the phosphorylase enzyme, it does not have any problem with breaking down of the linear glycogen here, or linear glucose, which has the 1-alpha-4 bond. So he will start just breaking down these bonds, 1-alpha-4 bonds. Now it will break it down until it reaches to here. Now this glucose residues, guys, if we will count from the branching side, so here's the branching side. This is the first carbon, first glucose, second, third, and this is the fourth. So whenever the phosphorylase enzyme reaches to the fourth glucose, starting from the branching side, it just stops phosphorylation. So after this section, it won't be able, or it can't be able to phosphorylase furthermore. Now, before moving that forward, let me explain you that the phosphorylase enzyme, whenever it breaks down this glucose molecule from here, it also adds one phosphor. So from here, it removes this glucose like this, and also adds one phosphor to glucose. And that phosphor is added to carbon number 1. So from here, there will be formation of glucose 1-phosphate by the help of phosphorylase enzyme. But the phosphorylase enzyme stops working whenever it reaches the glucose residues number, which is 4 from the side of branching. Now what happens then? I mean, if it reaches here and here, now we need to break down all those glycogen molecules. Will the glycogenolysis stop? No, of course. Now in this time, we have the debrancher enzymes. And the debrancher enzymes could be 1-alpha-4 or 1,6-alpha-1 6 amylase or 1-alpha-4 glucosidase. Now what will happen? The 4 remaining glucose residues will be debranched or broken down from the glycogen linear and branched side by the help of these enzymes. Of course, 1,4 will break down these linears, and 1,6 here will break down this molecule, which has the bond between 1 and 6 at the branching section. So this is how the debrancher enzymes will be breaking down the remaining 4 molecules here. And then again, we'll have the linear molecule, and the phosphorylase will keep working up to 4 glucose residues to branching side, and then the reaction will keep repeating. So now let's sum them up. Here we have the glycogenolysis. First enzyme which is necessitated is phosphorylase. It is converting the glucose residues to glucose 1-phosphate, and the other thing, it stops in 4 glucose residues from the side of branching. Next, the branched glucose residues will be broken down by debrancher enzymes. So, in deficiency of these phosphorylase alkali, let me remind you one more thing here, that the phosphorylase will positively or activated by the phosphorylase kinase. So I'll just pyruvate kinase, so phosphorylase kinase. So in deficiency of each of these enzymes, such as phosphorylase kinase, phosphorylase, debrancher enzymes such as 1-alpha, alpha-1,4 glucosidase, and alpha-1,6 amylase, there will be development of metabolic disorders, which are called in general the glycogen depot disease or disorders, which we'll discuss in pediatric in a very big detail. So for now, and from here, the only things which you have to remember is that there are debrancher and brancher enzymes, phosphorylase enzymes, and then the UTP, UDP, UMP, and those what we speak in the gluconeogenesis. So this is all about the glycogen synthesis, and glycogenolysis. Next we'll discuss about other topics, and till then, goodbye.